Welcome to this explainer. Today, we're diving straight into the epic, fast-paced saga of how scientists actually uncovered the fundamental architecture of the universe itself. I mean, think about it. Literally everything you see, touch, and breathe is built on a microscopic foundation that took brilliant minds decades to decode. So, we're going to unpack that whole journey, breaking down exactly how we went from completely misunderstanding matter to mapping out its ultimate power system. So, what exactly is the hidden architecture of the universe? And how on earth did we unlock its secrets? Let's dive right into this. For the longest time, humanity was practically in the dark about what actually made up the physical world. Sure, we knew things had mass and we knew materials reacted with each other, but the actual blueprints of reality, they were completely hidden in plain sight. Unlocking those secrets required a massive shift in how we viewed solid matter. To make sense of it, let's look at this timeline. We can basically break this evolution down into three distinct eras. First up, Era 1, the indivisible era. Back then, atoms were thought to be just these unbreakable, tiny little particles making up all matter. End of story, right? Well, not quite. As our tools got better, we smashed right into Era 2, the discovery era. Scientists shockingly uncovered a whole hidden world of subatomic particles just lurking inside the supposedly solid atoms, which naturally led us straight to Era 3. The structural era. Once we found the particles, the new game was mapping exactly how they all fit together. All right, let's move right into Section 1, Rutherford's gold foil clash. Enter Ernest Rutherford. He was a pioneer who decided, you know what, let's test the absolute limits of these newly discovered particles with what would become a totally legendary experiment. Step 1, he fires a barrage of high-energy alpha particles. Step 2, they strike an unimaginably thin sheet of gold foil. Now, everyone expected these heavy particles to just tear straight through, like a bullet through tissue paper. And yeah, most of them did. But Step 3 is the shocking deflection that literally changed physics forever. Now, what's absolutely wild here is that some of those particles actually bounced straight back. And these incredible deflections proved one massive thing: the existence of the nucleus. Rutherford realized that the only way a fast-moving, positively charged alpha particle could ricochet backward was if it slammed into something incredibly dense and positively charged, because, as we know, like charges repel each other. This totally shattered the old model. The atom wasn't some soft sphere. It was mostly empty space with all its power packed into this tiny, dense, positively charged center. So, monumental breakthrough, right? Rutherford found the core. But wait. Almost immediately, the scientific community realized his model had a fatal flaw. And I mean a flaw so severe it mathematically threatened the very stability of the entire universe. So why doesn't the atom just self-destruct? Well, the glaring issue was the electrons. Scientists quickly realized that if these negative electrons just revolved around the positive nucleus, like planets orbiting the sun, classical physics says they'd constantly radiate energy. And if they're radiating energy, they're losing momentum. If they lose momentum, they don't just stay in orbit, they'd enter a death spiral and collapse right into the center. If Rutherford's model was 100% correct, every single atom in existence would just blink out and self-destruct in a fraction of a second. But obviously matter exists, so something huge was missing. Which brings us to Section 2, Bohr's stable energy shells, the 1912 upgrade. To save the atom from this theoretical total collapse, a new hero steps in. Niels Bohr in 1912. He brilliantly proposed an ultimate stabilization technique with two main postulates. First, discrete orbits. He theorized that electrons don't just fly around randomly, they revolve in unbreakable, specific paths, energy shells labeled K, L, M, and N. And second, energy conservation. As long as an electron stays in its stationary orbit, it absolutely does not radiate energy. It just coasts. Perfectly stable. This elegantly solved the stability crisis once and for all. And this perfectly illustrates the clash of the two models. Over on the left, you've got Rutherford's model, unstable, energy-draining planetary orbits practically begging to collapse. But on the right, you see Bohr's model, stable, discrete energy shells with zero energy radiation, zero collapse. Bohr essentially handed us an atom that could actually survive long enough to, build the universe. Now let's get into Section 3, decoding atomic power levels. With the physical structure of the atom finally stabilized and mapped out, the next step was figuring out how to categorize it all. Scientists needed to decode the properties of these elements through atomic calculations. First up is the atomic number, universally represented by the letter Z. It's super simple, but absolutely crucial. The atomic number is just the total number of protons located right there in the nucleus of an atom. This number is literally the atom's unique fingerprint. If you change the number of protons, you physically change the element itself. Building directly on that, we have the mass number, represented by the letter A. If the atomic number tells you exactly what element you're dealing with, the mass number is basically the total weight class of the atom. Since electrons are incredibly light, almost all of an atom's mass is sitting right in that dense nucleus. So, the mass number is calculated simply as the total sum of the heavy particles, protons plus neutrons. Think of this table like the ultimate character stat card for the universe. It shows how Z, the protons, plus N, the neutrons, equals A, the mass number. The math is super straightforward, but it's incredibly powerful. Knowing just the number of protons and neutrons unlocks the exact mass number of literally any element in existence. As you can see, if you have two of these numbers, you can always easily calculate the whole shebang. Okay, but there is still one minor practical problem. To accurately measure and compare the mass of all these drastically different elements, from super light hydrogen to incredibly heavy uranium, scientists really needed an ultimate, universally accepted benchmark. They needed an anchor for their scale. And the magic number they collectively landed on? 12. Specifically, they chose carbon-12 as the absolute gold standard for the atomic mass unit, or AMU. They essentially said, look, let's take carbon-12, define its mass as exactly 12 atomic mass units, and measure everything else relative to that. Why carbon-12? Well, because it's widely accepted, highly abundant, and perfectly suitable for all comparative calculations. It finally provided a totally reliable, stable scale against which the power levels and mass of every other element could be cleanly measured. And that really brings us to the end of our journey in today's explainer. We've gone from thinking of matter as indivisible solid blocks, to the wild discovery of a dense nucleus, to Bohr's perfectly balanced energy shells, and finally the math that lets us categorize the whole thing. But I want to leave you with this. With the ultimate power system of the atom decoded, what other fundamental secrets is the universe hiding in plain sight? If the very atoms you are made of are this deeply complex and beautifully structured, what other hidden architectures are out there right now, just waiting for us to unlock them? Keep questioning, keep learning, and I'll catch you next time. Section 2, Anatomy of an Atom. Let's actually zoom in and see what's living inside that dense little core. So looking at the anatomy, the contrast here are just wild. Inside that hard central nucleus, you've got protons, which carry a positive charge, and neutrons, which have no charge at all. They both weigh 1 atomic mass unit. But then you have the electron zipping around the nucleus in these imaginary tracks called shells. The electron is negatively charged, and get this, it is 1/1837th the mass of a single hydrogen atom. That is practically nothing. It means basically the entire weight of an atom is crammed right into that tiny central nucleus. Now, how do we tell these atoms apart? That's where these numbers come in. The atomic number is essentially the element's ID badge. It's strictly the number of protons in the nucleus. And since atoms are normally totally neutral, that also perfectly matches the number of electrons flying around outside. The mass number, though, that's the heavy lifter. It's literally just the total sum of the protons plus the neutrons packed together in the core. But nature loves throwing us a curveball, right? Enter isotopes. You can actually have atoms of the exact same element that weigh completely different amounts. Crazy, I know. Since the atomic number defines the element, the protons have to stay exactly the same. But the neutrons, they can vary. Take regular hydrogen, for example. 1 proton, 0 neutrons. But its isotope, deuterium, has 1 proton and 1 neutron. It still acts exactly like hydrogen, it's just a little heavier simply because it has that extra neutron hanging out in the core. Moving on to section 3, electrons and valency. Let's step out of the nucleus and look at those outer shells, because this is where the real chemical magic happens. Okay, 8. 8 is the absolute magic number here. In chemistry, we call this the octet rule. Basically, every single atom is just desperately striving to get exactly 8 electrons in its outermost shell. Why? Because that gives it the perfect stable setup of a noble gas like argon. Noble gases are totally chill. They naturally have 0 valency and don't need to react with anything because they're already perfect. Every other element out there is just constantly hustling to reach that exact same state of chemical zen. So how many electrons can actually fit in these shells as you move outward from the nucleus? Well, there's this really elegant mathematical formula, 2n squared, where n is the shell number. The first shell can only hold 2 electrons. The second holds 8. But when we get to the third energy level, the m shell, we plug 3 into our formula. 3 squared is 9 times 2, meaning it can hold a massive maximum of 18 electrons. But remember, no matter how huge that capacity gets, an atom still only wants a max of 8 in its very outermost layer to actually be chemically stable. And that desperate quest for 8 outer electrons determines what we call valency. It's the number of electrons an atom will donate or accept to hit that noble gas configuration. It literally dictates the atom's entire chemical personality. Metals, for instance, typically have just 1, 2, or 3 outer electrons. For them, it's way easier to just ditch those electrons and drop down to a full, stable inner shell. Nonmetals, sitting at 5, 6, or 7 outer electrons, they're the thieves. They want to accept or steal electrons to complete their set of 8. This constant giving and taking, that is the engine driving every single chemical reaction. Which brings us perfectly to section 4, chemical bonds explained. When these atoms are desperately trying to stabilize, they don't do it alone. They form relationships. So when atoms do this little electron dance, they generally form 2 very different kinds of bonds. First up, ionic bonds. This is a stark, absolute transaction. Take sodium, which has 1 extra electron to lose, and chlorine, which desperately needs 1 to gain. Sodium just hands its electron over to chlorine. Now sodium becomes positively charged, chlorine becomes negatively charged, and because opposites attacked, they lock together into a super strong ionic bond. This creates tough compounds like magnesium chloride that are awesome conductors of electricity. Covalent bonds, on the other hand, are a lot more cooperative. Neither atom really wants to give up an electron entirely, so they just agree to share pairs of electrons between them. Because they're just sharing, covalent compounds are generally neutral, their intermolecular forces are a lot weaker, and they have much lower melting and boiling points compared to those tough ionic compounds. All right, final stop, section 5, nuclear fission and fusion. Time to look at some seriously immense forces hidden right in the center of the atom. We're leaving the chemical bonds of the outer shells behind and diving back into the nucleus, because the forces holding that tiny core together are frankly mind-boggling. Look at how these 2 opposing nuclear forces operate. First, nuclear fission. This is when a massive, heavy nucleus, like uranium, gets smacked by a slow-moving neutron. It violently splits apart into lighter pieces, releasing a colossal amount of energy. This is exactly what we harness in our nuclear power plants and atomic bombs. But then you have nuclear fusion, which is basically the exact opposite and somehow even more intense. Instead of splitting heavy atoms, fusion violently crushes tiny light elements, like hydrogen, together until they fuse into a heavier helium nucleus. That reaction unleashes so much sheer energy that it literally ignites the stars. It's the exact same massive power source fueling our very own sun right now. So, wrapping up this explainer, I want you to just sit with this amazing reality for a second. The atom used to just be this indivisible philosophical concept, but today, we know that tweaking its structure taps into the absolute most extreme forces humanity has ever discovered. From the medical miracles of using isotopes like iodine-131 to selectively cure thyroid cancer, all the way up to the staggering nuclear fusion burning inside the sun, this tiny, microscopic speck holds the greatest forces in existence. It really leaves you wondering, doesn't it? As we keep digging into these subatomic secrets, what other unbelievable cosmic cheat codes might we unlock next?